You got it. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. I thank you for these students. Just ask you bless this class. Help us to learn more about your creation together today, Lord. In your name I pray. Amen. If you're close to the back, if you wouldn't mind, could one of you on each side close those doors? Because as fascinating as the conversations are in those hallways, I don't want to hear them. You know, it used to be when somebody was talking to themselves in the hallway, we thought they were crazy, but now we just know they have a cell phone, you know? So, all right, so let's do it. So this is a pretty standard find the angle between two vectors question. To do this, we should notice that the length of A is the square root of 4 squared plus 0 squared plus 6 squared, which is the square root of, 16 plus 36, whatever that is. The length of B is going to be the square root of 1 squared plus 1 squared plus minus 8 squared. And that is the square root of, well, I suppose 2 plus 64. So we got, square root of 52, and over here the square root of 66. All right. And I'll just leave them like that because making them into decimals just makes errors for us anyway. Now, what's A dot B? A dot B is the dot product of A and B. We can calculate this. So here we go. 4, 0, 6, dot product with 1, 1, minus 8. It is unfortunate that your book underemphasizes this material. Yeah?
For the test, would you want us to leave it as square root of 52, square root of 66?
That would be fine if that was, I mean, it depends on the question. But yeah, probably that'd be okay. I probably at the start of the test will say something along the lines of, I'd like answers as decimals. Just because what I don't want to have happen is have an answer which people write as like minus 3 times the square root of 66 divided by 7 plus the square root of 74. Like, that might be the answer, right? But there's like a couple different ways to write that. And then if I'm grading, it's much easier for me if you actually make a decimal number. But also on the test, it's unlikely I was asked this. Like, I'm most likely going to give you, if I was asking a vector problem, I'd probably give you one with units. Like this is a little bit kind of a math version of the problem, right? We probably should put like meters on this or something to make it more physicsy. I'm going to go on though. Okay, so the dot product, remember we defined last time, means we multiply this times this, that times that, and that times that, and add them together. So that's just the definition of dot product. So 4 times 1 plus 0 times 1 plus 6 times minus 8. So it looks like the dot product of A and B is equal to what? I heard a negative what? Negative 44? Okay, but on the other hand, there's a theorem which says it's equal to A times B, the length of A, times the length of B, times the cosine of the angle we're trying to find between A and B, all right? And so we can then figure out what that angle is. This is just a heuristic picture. I really don't know what A and B actually look like without drawing coordinate systems and thinking through it. And I don't even need to do that, so I'm not going to here. But you can see that then theta should be equal to the inverse cosine of A dot B over A times B, which in this case is the inverse cosine of minus 44 over the square root of 52 times the square root of 66. And so that's why I didn't really care about finding the decimal approximation for those, because that wasn't actually what I was interested in, right? Like, I'm interested in the angle. So the square root of 52 and the square root of 66, these are just, it's not the answer, right? It's a step towards the answer. The answer I do want to give as a number, though, in here. So we just got to calculate the inverse cosine of that thing and figure out what it is. So let's see, what do we get? Beware of degrees versus radians. We want degrees, okay? So like I'm in radians right now, which is annoying, you know? I got to change it to degrees. All right, we're in degrees now. I mean, I'm in degrees. I don't know what you're in. Let's see here, divided by, I need myself a square root of 52 times 66. All right, if I did this right, my calculation is that that angle trash can. I don't know what, I'm lost. I have no trash can to throw markers into. I don't know what to do. It's no good. Yeah, I don't know. This is kind of debatable. I may hit you. Nah. So I got a 138.7 degree angle right there. Is that what you guys got? Yeah. Hooray. All right, so then that's part A, right? That was the answer to part A. How about part B? To find the answer to part B, what we got to do is what's A plus B? That is, let's call that C, right? So the C vector, which is A plus B, is 5, 1, minus 2. And let's say that A minus B is the D vector, just to give it a name. A minus B, well, there's just all kinds of new noises in here today. I don't even know how to characterize it. It's the hurricane. It's a hurricane, not a hurricane. Let's see here. A minus B. So I got a 3. I got a minus 1. Looks like I got a 14. Because A minus B, so it's like 6 minus a minus 8, which is like 6 plus 8. So those are my A plus B and A minus B vectors. So you can calculate the length of C is the square root of 25 plus 1 plus 4. The length of D, the magnitude of D, is the square root of 9 plus 1 plus 14 squared, which is whatever that is. Is that 192? No, 196? I have a calculator in my hand. What am I doing? What's wrong with me? You guys don't care if I can do arithmetic or not. We got nothing to prove here. All right, so whatever that is, looks like C is the square root of 30, and the magnitude of D is the square root of, looks like 206. Okay, so then what's C dot D? Well, it's equal to CD cosine of the angle, let's call it beta. That's the angle we're trying to find. This is my C vector. This is my D vector. C I said was A plus B. D I said was A minus B. Just to give it a name. I'm calling that angle beta. We're trying to find beta. That's the answer to part B. So what's C dot D? What's the dot product of C and D equal to? You just got to take 15, right? We've got 15 minus 1, 3 times 5, minus 1, minus 28, is equal to, well, the square root of 30 times the square root of 206 times the cosine of beta. So there we go. We got that the beta is equal to the inverse cosine of, minus 29. Is that minus 14? Is that minus 14? For the numerator? All right, so what's that give us? So I get a minus 0.178 blah, 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 blah to put into the inverse cosine. I calculate 100.3 degrees. There you go. So I thought I should do another example like this because, you know, I know there's not too much of this to go on in the book. So it's probably a good idea for me to actually do some for you so you can see it, and So now we've done that. So let's get back to the projectile motion then. So I'm gonna derive something for you, and then I'll take your homework questions. Okay, that's my my plan here. My derivation should take about 5 minutes or so. So if you want to be thinking about which homework question you want to ask about while I'm doing this, that'd be awesome. Let's see here. Can I think I can erase this, right? Yeah. Can I erase that now? Okay. Oh, I almost forgot. Leaving your quizzes in my office has gotten me all out of order. I was going to talk to you guys about the quiz. So let's do that before I forget. All right, that shouldn't take but a minute. It's like I'm forgetting something. Here it is. I'm going to do that for a minute. So problem 1, I ask you to find the displacement given 2 events, right? 2 positions. You're fine. All right. Let me see if I can make this a little bit bigger so we can all see. All right. So to start with, to find the displacement, I take the final position minus the initial position, right? That gives me 30, 11, 5 minus 0, 1, 15. So we just subtract the x from the x, the y from the y, the z from the z, and out pops 30, 10, minus 10 meters. Or if you prefer, you could write it 30 meters, comma 10 meters, comma minus 10 meters. It's all good. All right? So that's part A. Part B, you're supposed to find the average velocity for the toy car. So you take the displacement divided by the time. The time is the 10 seconds minus the initial 0 seconds. So the time elapsed, I can almost say that today, is 10 seconds. And the displacement, well, you figured that out in part A, right? So the average velocity is a vector. And in fact, it is 3 meters per second, comma 1 meter per second, comma minus 1 meters per second. All right? Any questions about this? All right, good. Of course, you could factor out the meters per second and just write it off to the side if you wanted. The same thing. Problem 2, actually a little bit more interesting. Problem 2, we're asked to study a car that's initially having a speed of a velocity of 100 meters per second. The car brakes. That's misspelled. Sorry about that. Oh well, none of you cared. Still none of you care. All right, good, fine, it's great. Don't tell the English department. Anyway, so the car is decelerating at 5 meters per second squared. It's got a negative acceleration of 5 meters per second squared. We're supposed to find the stopping distance and also the time it takes. So the stopping distance is conveniently calculated from the constant acceleration formula, the so-called timeless equation, right? And so we know that the final velocity is 0. We know that the initial velocity is 100 meters per second. So we got to take 100 meters per second squared divided by twice times minus 5. The minuses cancel. We got a meter squared per second squared upstairs. We got a meters per second squared downstairs. So the second squareds cancel. And we're left with a unit of meters overall. And 100 squared divided by 10 is just 1,000. So 10,000 divided by 10 is 1,000. So we got 1,000 meters. That's the stopping distance here. The time, well, the time we can calculate from the velocity equation. Velocity is the initial velocity plus acceleration times time. So if I solve for the time elapsed, I get the final velocity minus initial velocity divided by the acceleration, which ends up being 20 seconds. So that's how you do it. And any questions about that? I think the homework problem we worked at the start of last class was considerably like trickier, right? So with that, I'm going to put this away then. I will post this solution in Blackboard for you guys. I just haven't yet, but I will. Hopefully soon. So let me put the lights back on here. All right, so I pulled this out of the thin air last time, but I should actually, yeah, I'll fix that for you. I know it's kind of a pain. That's the bad thing about using that stupid projector is then I get all out of order. Ah! Excuse me. So what I'm about to derive here once I get rid of this problem here is the so-called range equation. All right, so what is the range equation about? So whenever we talk about an equation in physics, context is so important. What's the context of the range equation? Here's the context. Projectile motion where the initial and final heights are matching. So just to let me draw a schematic for what I'm saying. So you got a plane, right? And you got two mountains, right? You got one guy with a bow and arrow here, woohoo, and he goes like that. And suppose that is the same y before and after, the final y, the starting and the finishing height of the arrow's trajectory. Suppose they're at the same height. In this case, the range equation applies. All right? What you could not apply the range equation for is the trajectory I'll draw in red in just a second here. If you start at y naught, but the end of your motion is like different, like this, then in this context, range formula does not apply. No apply. You can tell the English department I said that. So, es no apply. Es no bueno. No? All right. That's about all I speak. I watched some Sesame Street as a child. That's pretty much it. But, okay. So the question then is this projectile motion, we'd like to study it, okay? And here's the deal. So this is the situation, and the situation is this. We're just going to, for simplicity's sake, suppose that y naught is equal to 0, all right? And so we've got this initial velocity v naught. It's fired at an angle of theta, all right? And so we're going to have projectile motion then. In other words, motion under the constant acceleration of gravity downwards, like so, all right, over to there. This distance is called the range, which we'll use a capital R for. So let's work it out. What is the range as a function of the initial speed v naught, and the angle at which the bullet or whatever is fired, theta. We're neglecting what? Lots of things. Motion of the Earth, right? The Earth is not flat and motionless. It's actually spinning, right? So if you neglect the spinning of the Earth, that can actually make a difference. There's a fairly famous naval battle with the British where they corrected for something called the Coriolis force in the opposite way in the southern hemisphere, and in so doing shot like 15 kilometers the wrong way. Because the Coriolis force is different in the northern and southern hemispheres of the Earth, and so it has to do with the Earth like turning out from underneath you as you're shooting something. That's essentially what the Coriolis force is describing. So we're neglecting that sort of thing, the Earth spinning. We're also neglecting something much more mundane, which is air friction, right? We have no way to account for that. So we're neglecting air friction, neglecting, frame effects like rotation of the Earth, and we're just assuming that the force of gravity is constant and it's giving us an acceleration of minus g. That's projectile motion. Given all those terms and conditions, we need to write down the formula. So here's the formula. First of all, x is equal to v naught cosine theta. I'm sorry. Un moment. X is equal to x naught plus v naught cosine theta times t. And the reason I write that down, it's very simple. So this is the initial position, which I'm saying is x naught. I mean, you could make it 0 if you want. I'm just calling it x naught for the moment. So we have x equals to x naught. And why the v naught cosine theta? So if we think about the velocity vector, right, this velocity vector, it's got two pieces. It's got this piece here, which is v naught cosine theta. That's the horizontal part of the velocity. And there's also a v naught sine theta. That's the vertical part of the velocity. So when we have projectile motion, if I can find a marker to sacrifice. This one looks like it had a good life. So if I give it some horizontal velocity like that, it survived. I guess it's meant to live on another day. But whatever horizontal velocity I gave it to start with, it keeps going over at that rate. That v naught cosine theta, it just keeps going. There's no x acceleration. In contrast, the y velocity varies with time, right? So, I mean, what's the formula for the y velocity while we're at it? Vy, it's equal to v naught sine theta, because that's the initial y velocity, right? And then minus gt. So this is velocity as a function of time. Those are the kinematic equations for the y velocity, the x position. How about y? What's the formula for y? Well, we put y naught equal to 0, so I guess I've got that. So what I have there is I'll have v naught sine theta times time minus 1/2 gt squared. So there you go. These are your kinematic equations for projectile motion. Now we just got to think about analyzing. We can use some symmetry here, right? If you think about it, how much time does it take to get up to the top of the motion? If we were to think about that, how long would it be until we got up to like the zenith of the flight? Sometimes we ask questions about the max height. So what's that? This would be, that would be y max, right? What does the velocity look like right at that top point in the flight? 0 for, yeah, 0 for, so it's 0 for y, and how about the x? Yeah, so right, the velocity is actually just v naught cosine theta 0, if we write it as a vector. It's got 0 y component, and it's just all in the x. Okay? So if we wanted to find the time here, let's call that time t star, to give it a label. How would you figure out what t star is, the middle time? I think you guys just told me. It's where the velocity, the y velocity is 0, right? So to figure out t star, we should say that 0 is equal to v naught sine theta minus gt star, right? That's the condition for the middle time. And so we can solve that for t star. What's that tell us t star is the time to the top of the flight? T star is v naught sine theta over g. Then what do we do? Well, okay, great. That's the time to the middle point. So by symmetry, what's the total time? What's the time of flight over here? What's this? T total, if you like. If you see the symmetry that I see, you can see that should just be twice t star, right? It takes the same amount of time for the baseball to fly up to its top as it does for it to fall back down, right? There's no asymmetry there. It's the same time up as it is down. you could imagine throwing a baseball like straight up. It would take just as long for it to get to the point where it turns around as it does for it to fall back into your mitt, or onto your head, whatever. So I think you should be able to see that that's twice t star, right? And that's significant. I mean, so we have this t star, we've got this total time, and we can use these two times to figure out a couple different things, right? We can figure out the max height of the projectile, and we can also figure out the range. Let's figure out the range. What's the range equal to then? So that's the x distance. We could also identify that that's x minus x naught here. And so that would be v naught cosine theta times t total, right? But what is that? That is v naught cosine theta times what? 2t star. What is 2t star though? Looks like we've got 2 v naught sine theta over g. Now, we can rewrite that. That's v naught squared times 2 sine theta cosine theta, all divided by g. So one of you asked me, like, what trigonometry do I need to know in here? All of them? That's not, I don't think that's actually the case. I mean, I would say that to a Calculus 1 student here. 131 student. If you're a 126 student, how much trigonometry do you do in 126? The answer should be none. If the answer is not none, your instructor is misbehaving. And I respect that. But even I don't do trigonometry in 126 because you're not supposed to. It's got a trig lobotomy. In contrast, we do not have a trig lobotomy here. We do trigonometry. For the most part, the kind of trigonometry that I just did over here, that's the biggest part, just seeing the relation between the hypotenuse, which was length v naught, and the adjacent side, which was v naught cosine theta, and the opposite side, which was v naught sine theta. That's the lion's share of the trigonometry we do in here is just right triangle trigonometry. Just the relation sine, cosine, hypotenuse, adjacent, opposite side. That's a lot of it. On occasion, we need a trig identity. But you guys also have a formula sheet, right? You can't really put the concept of what I just did over here on a formula sheet. Like, you got to understand that for yourself. I mean, you could write the picture down, but to own it, you have to own it for yourself, right? But the thing I'm about to write down, you can put on your formula sheet. You own it or not, it's just something you got to be aware of. And that's the fact that 2 sine theta cosine theta is actually just sine 2 theta. Right? So this is v naught squared sine of 2 theta over g. And there you go. That's our beloved range formula. The range is equal to v naught squared sine of 2 theta over g. And now you can see mathematically that the longest, the biggest range we could have would be when that sine term is 1, right? How can you make that sine term be 1? What angle do you have to pick to make sine of theta, sine of twice theta to be 1? Yeah, 45 degrees, right? Because the sine of 90 degrees is 1. Of course, you could also do minus 45 degrees. That would also work, right? Because the math can't really tell whether you're pointing this that way or that way. Like either the 45 degrees or the, well, not minus 45 degrees, but rather, what's this angle over here? What would this be? That's not minus 45, that's 135 degrees, right? Actually, if you put minus 45 degrees, I don't recommend shooting cannons minus 45 degrees into the ground, right? It won't go well for you. You generally want to shoot above the ground, just point of, safety. All right, so anyway, that's the range formula. You can see 45 degrees is the best we can do. How about the max height formula? Because we can do that too while we're at it, right? What's the max height? So that would be y at t star, right? The height at t star. Since I put y equals 0 as our initial height, this is actually the height, the change in y, the distance traveled upward. And so y of t star is v naught sine theta. Where was I? V naught sine theta times t star minus 1/2 g t star squared. And if we plug in t star, what was t star? V naught over sine theta over g. Try to get the point here, guys. So if you look at that, you've got the, what do you got here? Oh, I messed it up. Sadness. What's wrong with me? Look at this. Good night. All right, no. This is supposed to be v naught sine theta over g. So what happened? We multiply this out. What we got? We got ourselves a v naught squared sine squared theta divided by g minus, g over 2 v naught squared sine squared theta divided by g squared. So you see the g and the g squared, they cancel out. And the algebra here is that the second term is actually the same as the first term, just with a half, right? So the pattern here essentially is like Pac-Man minus a half a Pac-Man. So that just leaves you with a net of half a Pac-Man. And algebraic simplification here, we just have v naught squared sine squared theta over 2g. There you go. That's the height to zenith of the flight. So how do you get the maximum height? How do we make sine as big as possible? Because if we make sine as big as possible, the sine squared will also be as big as possible. If you think about it, pi over 2, right? Does that make sense? If you fire the cannon straight up, it goes to the maximum height. Right. Not a really smart trajectory to plot for your cannon, but if you just want to really show how high it can shoot, well, there you go. Shoot it straight up. Anyway, I'm not telling you anything terribly exciting here. So these are ideal formulas for ideal cases. Now, a lot of times I'll ask you guys a more interesting question in class or in a test or something like that. We might have a question like a basketball player, right? He's on the court, and he has a certain height, and he shoots the ball given a certain initial speed and a certain angle. Can he make it into the net? Something like that, right? And so the questions that we'll often ask don't allow you to use the range formula directly. You actually have to sort through these formulas for that particular case. Most of the questions that you run into are like that, all right? You can't just quote unquote plug and chug, Let's look at an example like that. So is there a question about homework in particular you guys like me to fuss with? Yep.
Homework, but could you use that same formula for max height if the endpoint isn't the same, like the height of?
Could you use it for the max height if the endpoint was not the same?
Like it's not the same height as the beginning point, so you can't range.
So what do you guys think? If the endpoint is not the beginning point, will that formula still give us the max height? I think so, right? Because it was based on looking for where the y velocity is 0. And no matter what kind of scenario you think about, that top point in the flight is where the y velocity is 0. So yeah, I think you're right. That would still be the case. The thing you got to be careful for is interpretation. Like I put y not equal to 0, you know? So if you're, you know, if you're, you know, you're whatever you're throwing, if it starts out at a meter and then you throw it upwards, then the question is, what kind of distance are you talking about? Are you talking about the distance from the hand, or are you talking about the distance from the floor in terms of vertical height? That's the issue you got to watch out for, that my formula hasn't quite addressed directly. So like this, that would give, that what I wrote there gives us the max change in y. I mean, this is the change in y from wherever you're starting. That is true. Here, let's make up a problem. Now, sometimes you can use the range and the max height formulas just as a sort of, if the question is like yes or no, you could check the range and the max height formulas just as a sort of, as an entryway to, do I need to do a more sophisticated analysis, right? Like it may be that checking the range formula and the max height formula immediately rule out the possibility. So let's see if I can come up with an example of that. So, you know, suppose you've got a cannon and it's firing the bullet with velocity v naught, right? And there's a there happens to be a I don't know, like Madara is here, and he's put some sort of gate that's giant and very, very tall. Gate. So this gate is there to block the bullet, right? And suppose that this gate is 500 meters high. 500 meters tall. And suppose that this distance is, I don't know, 200 meters, right? And suppose, further, that the cannon shoots its projectile, its cannonball, with a velocity of, I don't know, let's say 20 meters per second, just for the sake of discussion. Suppose v naught equals 20 meters per second. So given that, you could do some quick calculations to see if it's even, so my question is it possible for that projectile to clear the wall? Can it get over? Is it going to hit the wall, right? Then you could ask the question, where does it hit the wall, if it does hit the wall, or does it clear the wall? But to start with, we can just ask the question, does it clear the wall? Well, if the max y for the projectile is what? If it's less than 500 meters, it's not going to clear the wall, is it? So what's the max y given 20 meters per second to start with? Formula I just erased. So v naught squared sine squared theta divided by 2g. So now we want to just be as greedy as possible, right? So let's make that, again, this is just back of the envelope kind of calculation. Suppose it was, I don't know, I mean, let's make theta be 90 degrees just for giggles and see what it does to us. So this is, hypothetical. Because this is the absolute largest height we could possibly attain with this velocity, right? Which would be what? 20 meters per second squared divided by 2 times 9.8 meters per second squared. So what's that height? We got 400, right? 400 meters squared per second squared in the numerator divided by about 20 meters per second squared downstairs. This is just an approximate calculation anyway, so I might as well be kind of a little bit sloppy. And what's that give you? That gives you, well, looks like 20 meters. Well, that does not look very hopeful. Right, so the max height that such a cannon can attain is 20 meters. It's definitely not going to clear this 500-meter gate. So what if instead of having 20 meters per second, what if we had 200 meters per second? My question, my question is, if you double the, well, if you increase the velocity tenfold, does that make the maximum height 10 times bigger? What's the dependence on the maximum height and the velocity? It's not a linear proportion. Notice the square, right? If we make the velocity 10 times as big, it increases the height 100-fold. So if I had 200 meters per second, I would get 20 times 100, which would be 2,000 meters. Then we might be able to clear that gate. So let's make it 200 meters. So anyway, can I erase this? I just want to, this is a thought process that you might go through for a question. The range formula and the max height formula give you kind of best case scenarios that you can think about. All right? All right. So let's suppose it's 200 meters per second, and let's see if it actually clears that gate. Now, in order to make this problem make sense, I mean, you could pick whatever angle you like. Let's make this problem a little bit less ambiguous. Let's pick an angle, just so that we're not also thinking of that as a variable, because I know if there's too many variables in the problem, you guys lose track of what I'm doing. Let's make this angle be, what do you want it to be? 50? I'll take that. 50 degrees. Great. So if that's 50 degrees, then we have the following equations. X, and let's make this at x equals to 0, right? So x is going to be equal to 200 meters per second times the cosine of 50 degrees times time, right? That's my formula for x as a function of time. So the initial velocity times time, because there's constant acceleration, constant velocity motion in the x because the acceleration is 0. How about y? Well, looks like we've got 200 meters per second times the sine of 50 degrees times time minus 4.9 meters per second squared times time squared. Right? That's this equation right here, right? Just with numbers put in. Now, how do I decide whether or not the projectile clears the gate? What time am I interested in, and what inequality is interesting to us? I mean, like what time? I need to figure out this time, right? So that, let's give it a name. How about T-bar? I haven't used T-bar yet. There you go. So what would that particular time would satisfy a very certain, very particular equation, right? We should have x at time T-bar is equal to what? It was given in my diagram, right? The gate is 200 meters from where the projectile is being fired. So I should set x of T-bar equal to 200 meters. But what else is x? What else is x equal to? X is equal to 200 meters per second times the cosine of 50 degrees, right? Times the time that I don't know, this T-bar. Aha! So because we have constant velocity in the x direction, if we know a distance, we know a time. Just like that, right? Now we got to do the algebra, figure out what T-bar is. What's T-bar? Looks like it's going to be 200 meters divided by 200 meters per second times the cosine of 50 degrees. Well, the 200s cancel, right? And we got 1 over 1 over, yep.
Sorry, I got caught up in writing, but where did you get the 4.9?
Oh, that's g over 2. A very good question indeed. You could just as well write a half and 9.8 there, or just, I'm being lazy. So the 200s cancel, the meters cancel. We've got 1 over 1 over seconds, which is otherwise known as a second. And so, like, you know, here's some trigonometry for you. This is the secant of 50 degrees times the second. Now, I don't know if that's really helpful. Do you have a secant button on your calculator? Oh, you do? Oh, good. I don't know if I have a secant button on my calculator. I've definitely got a cosine button on my calculator. You know, just sitting there looking at me. Secant, not so much. So that's why, in fact, this formula, unless you've got, well, so one of you's got a fancy secant-enabled calculator, that's good. But I think for some of us, we really need to look at that for the sake of our calculator as this a second over cosine of 50 degrees. What is it? No? If I did something, let me know.
1.56.
I'm going to take your 1.56 and replace it with a 1.556, but yeah. I try to keep four numbers, you know, just to avoid round off errors as much as possible. Now, okay, great. That gave me the time to when the projectile hits the gate. Now, how do I decide whether it cleared it or not? I need to actually calculate y at that time. So what's y of t bar? What does this notation mean, guys? I'm using function notation, like f of x. So this is not multiplication of y by t bar. This is I'm saying I'm putting time t bar into the y function. All right? Just a comment. You know, physics is mathematical. And that's probably easier to notice with me than some other instructors, but it is. Let's see here. 50 degrees. T-bar, which is 1.556 seconds, minus 4.9 meters per second squared, times 1.556 seconds quantity squared. What does that give us? What is y of t-bar? Let me crunch the numbers here. 200 times the sine of 50 times 1.556. So that first term is like 238.4-ish. That's what I got. And then I'm going to subtract my calculation is 226.5 meters. So the legend looks like the legendary ninja will be safe on the other side of the gate. You know, like he's got this 500 meter tall gate. That's really quite a gate. You know how tall that is? Do you have any sense of what 500 meters is? Like, where is the Empire State Building in this picture? You're all New Yorkers, so that's what you think in terms of height, right? Okay, let me put Freedom Tower. Where's the Freedom Tower in this picture? How tall is the Freedom Tower in meters? How many feet is it? Lots. This is not helpful. Quick, someone Google Freedom Tower height. That is where that's the height. 275 feet. 275 divided by 3.281. You said 275? Yeah, so about 83. So here's the Freedom Tower. something like that. It's like less than 20% the height of this thing. Now, that said, the Freedom Tower is at about 83 meters, give or take. Well, 84 meters, about 84. We'll round up. We'll feel good about ourselves. 84 meters. And, I mean, imagine go put a little car antenna on top of it or something, you know? And then, so this hit at 226.5, well, that's like up here somewhere, right? That's actually where the projectile actually hit. About halfway up, a little less. So does it clear the gate? No, it does not. If you had like infinite speed, if you could launch the projectile with infinite speed, what height would it be at as it was trying to clear the gate? Like if I think about this as being the gate, right, and this is my cannon, and if I could launch a projectile with like as fast as possible, what does the trajectory look like? It does matter what angle, but what I'm trying to get from you guys is it would be essentially straight line, right? Yeah. So there's a sort of trigonometry involved in here. So that if that's 200 meters, then you know this what geometry here alone says that what would this height be? If this is 200 meters and that's angle's theta, what's this height? Assuming a right triangle. Which of the trigonometric functions is your friend here? You want your sine? You want your cosine? You want your tangent? Which one are we going to use? Let's call the thing we don't know y, right? Yeah, I heard a tangent. I like that. So the tangent of theta is going to be opposite over adjacent, right? So this suggests that y is something like 200 meters times tangent theta. That's just sort of a geometric. I mean, that's not actually where the thing will hit for finite velocities, right? Because for finite velocities, it actually drops off because of acceleration due to gravity, right? But that would also give us a kind of quick estimate of where it could possibly, best case scenario, hit. So if we use 50 degrees, is there any hope? Is there any speed? Like 200 meters per second didn't work. If we made it, 200,000 meters per second, would it help? Well, we could check the trigonometry really quick and just see if it's even possible. What's 200 meters times the tangent of 50? What's that? 238? See, so we didn't need to do everything we just did. We could have gone with this idea and avoided the whole bunch of kinematics that we did if we just were willing to invest a little bit of time and intuition into some conceptual physics. I'm not suggesting that that's the way you should think about doing these. It's just another way of thinking, yeah? If you were to do such a thing on the test, you probably better explain it to me. Otherwise, I won't know what you're doing. Yep. It's funny. So we were doomed. Doomed, I say. And it's actually kind of interesting is the gravity hasn't really done much to the motion yet, right? It's dropped off. Instead of being at 238, we were actually at 226. So gravity's caused the motion to sort of deflect down just 12 meters at that point. It's kind of interesting. Well, anyway, the larger point here is we don't have to speculate. We have equations, kinematic equations. We just have to set them up and work through the math. That's all there is to this projectile motion stuff, okay? So, any questions about particular problem in the book or anything? Yep. On 40, you said on 40, what was it? Oh, did I not pass the roll sheet around yet? I'm sorry. Let's get that going. We are tick-tock, Hopefully that'll Don't leave before you sign that, please. Hey, hey, hey. Which one? Page what?
47, 70.
Page 71? Page 47. Problem 71. Oh, see, now you're going to make me work. All right, so this is the, so we had a cliff. We throw a stone vertically with a speed of 15.5 meters per second from the edge of a cliff 75 meters high. And the question is how much later does it reach the bottom of the cliff? And what's the speed just before hitting? What's the total distance did it travel? So which particular part of the question is vexing?
Well, I tried to do it as in like 2 parts.
Okay.
From the person's hand and back down to them, and then from the edge of the cliff to the ground.
Uh-huh.
To the north.
All right. Well, let's just start working through it. Maybe we'll figure out what it is that is tripping you up. Let me draw a picture. Here's person. Here's motion. And then what else did we know about this? So they said y is equal to minus 75 here. They put y equals to 0 up here. They did that to us, didn't they? So their picture, they've already set a coordinate system, have they not? And they said that the initial speed, v naught, was 15.5 meters per second. Does the x equation matter to this problem? It does not, right? It's just a vertical problem, so we can basically ignore the x. It's not complicated projectile motion. It's just up and down. So how much later does it reach the bottom of the cliff? All right, so here's the equations that we have to deal with. Y is equal to, well, 15.5 meters per second minus 9.8, oh, well, excuse me, 4.9 meters per second squared times time squared. I think I've forgotten a very important times time here, right? So there you go, that's the equation. Do we agree? This is the equation of motion? Yes, no? So the initial y is 0. The initial velocity is 15.5 meters per second up, right? That's why plus. If they said she threw the stone down with 15.5 meters per second, then I put a minus there, but I don't because it doesn't say that. And so that's the equation of motion. And then so to figure out, the part A is how much later does it reach the bottom of the cliff? We're asking the question, t equals what for y equals to what? What's the bottom of the cliff? Well, negative 75, right? So I'm trying to solve negative 75 meters equals to 15.5 meters per second times time minus 4.9 meters per second squared times time squared. I don't know about you, but I'm getting really, really sick of the units on this problem. Let's strip them off and just focus on the math. So there's a quadratic equation that we have to deal with here. And it's just, excuse me. Let's see here. I'll move that stuff to the other side. So I got 4.9 t squared minus 15.5 t minus 75 equals to 0. That's a quadratic equation. We know how to solve it. Let's solve it. So were you were doing what you did? What you wanted to divide it up into two parts. You wanted to calculate.
Because I thought once it started to come back down, there would be a different velocity.
I think you're right. So like what's going to happen? You could calculate the time it took for it to like come back to where it started. When you did that, this part